This lecture is on magnetic susceptibility and susceptibility-weighted imaging in MRI. It is best viewed after having seen the preliminary lecture on basic MRI physics, which I have called spin gymnastics and is also available for public viewing. This lecture is mostly graphical in nature, but it does contain a little bit of mathematics, 2 or 3 slides near the beginning of the lecture and another 2-3 slides of math in the middle of the lecture. The rest of it is basically a graphical explanation of this topic. The various subtopics that will be covered is what is magnetic susceptibility and the definitions of diamagnetic materials, paramagnetic materials, and ferromagnetic materials. Examples will be shown of materials that are found in human tissue that have different magnetic susceptibilities, and the effect of these different susceptibilities will be shown on MR images. There will be a discussion about the magnitude and phase components of an image and how magnitude and phase relate to magnetic inhomogeneity and magnetic susceptibility. This will move on to what are called susceptibility weighted images and some applications in neuroradiology. Towards the end, we'll look at some special consideration in analyzing the phase components of these images, and then there will be a short summary. Magnetic susceptibility is conventionally denoted by the Greek letter chi, and it is the degree to which a tissue magnetizes, symbolized by capital B subscript little t, when put into an applied magnetic field, B subscript naught. The formula for magnetic susceptibility is B subscript T is equal to the applied magnetic field times 1 plus the magnetic susceptibility. So at any given applied magnetic field, B, if a tissue magnetizes more than another tissue magnetizes, it has higher magnetic susceptibility. If chi is positive, the material is said to be paramagnetic, and the magnetic field in and around this material is strengthened by the presence of the material in the applied field, the induced magnetization. If chi is negative, the material is said to be diamagnetic. As a result of diamagnetism, the magnetic field in and around the material is weakened by the induced magnetization. Ferromagnetic materials have positive susceptibility and possess permanent magnetization even without an externally applied magnetic field. What is the magnetic susceptibility of tissues, contrast agents, and other MRI relevant materials? Most tissues in the human body are weakly diamagnetic and usually cannot be distinguished from one another on the basis of their susceptibility. Calcifications are relatively strongly diamagnetic and are the principal material that can be detected as diamagnetic in MRI. The paramagnetic materials that are relevant are blood and blood breakdown products, iron, gadolinium-based contrast agents, and probably melanin. What effect does magnetic susceptibility have on MR images, and on which images? Let's just work through the formula. If chi changes, then the magnetic field strength in tissue changes. And I'm going to use an approximation here. Instead of the formal formula, I'm going to change the induced magnetization to be approximately equal to chi times the applied field. So I've changed the term 1 plus chi simply to chi to simplify the math. And therefore, so 2 does the rotational frequency, because rotational frequency is proportional to the magnetic field that the dipoles experience. So the rotational frequency is equal to the gyromagnetic constant times the induced magnetic field. If there is a difference in rotational frequencies, then there will also be a phase difference. Since phase is equal to the rotational frequency multiplied times the interval at which the signal is measured relative to the excitation pulse. This is usually denoted as TE. So if we then substitute the formula, phase is equal to the gyromagnetic constant times the magnetic susceptibility, chi, times the applied field, times the equitime. If you follow through with this formula, you'll notice that differences in magnetic susceptibility are most apparent at the higher magnetic fields and at the longest TEs. So if you want a highly weighted susceptibility weighted image, do it at high field strength and with a long TE. In the next few slides, I'm going to work through some illustrative examples to show what happens when a series of adjacent voxels are in close proximity and have the same magnetic susceptibility, and what happens when the voxels are separated in space or when the susceptibility in one of the voxels changes. So we start with 5 voxels adjacent to one another, all given the same susceptibility. We put them in a magnetic field. The induced field in each voxel is the same because they have the same magnetic susceptibility. So the precessional frequency in each of these voxels will be the same. So the local field, the induced magnetization in each voxel is the same. The precessional frequency in each voxel is the same. The spins stay in phase. Since the magnetic field and the frequency is the same in all the voxels have the same intensity on the image. Let's separate these voxels out in space and then put something into the middle voxel that gives us a higher magnetic susceptibility. And in this example, we're going to put some red blood cells into the middle voxels. And red blood cells contain iron. Iron's paramagnetic, so it changes the susceptibility. It has a higher magnetic susceptibility than the other voxels in this slide. We put these voxels into a magnetic field, and the induced magnetization in each of these voxels is the same in the 4 peripheral voxels, but in the central voxel, the induced magnetization should be higher because it contains a paramagnetic substance, and therefore it should be brighter. However, the red cells are not uniformly distributed within this voxel, and so you get a non-uniform field in this voxel. And so even though the magnetic susceptibility is on average higher, the heterogeneous effects of the red cells in the voxel cause accelerated dephasing, and they cause marked signal loss in the voxel. And even though the induced magnetization is higher, this voxel will look darker than the other voxels. So these dephasing effects dominate, and the signal is lower in the middle voxel compared to the other voxels. What happens when the magnetic susceptibility is lower in the central voxel? For example, if calcifications are present in that voxel. Well, because calcium is diamagnetic, the magnetization in the voxel is less rather than more. And because calcifications are typically particulate, you have non-uniformity in the voxel, which leads to further dephasing and signal loss. So the net effect on the signal intensity is the same. Let's look at this graphically. We have 5 voxels separated in space, placed in a magnetic field. We create lower magnetic susceptibility in the middle voxel by placing calcifications in the middle voxel. And this combined effect of diamagnetism, lowering magnetic susceptibility, and the dephasing due to the presence of the calcium particles ends up causing the voxel in the middle to be darker than the peripheral voxels. It is the heterogeneity that is the dominant effect leading to the dephasing and the signal loss, regardless of whether the local field in that middle voxel is decreased or increased. Let's now place the voxels adjacent to one another. We have the same model of 5 voxels, 4 peripheral ones and a central one. In this particular case, we've placed red cells in the middle voxel. And as previously shown, this leads to a change in the magnetization, but also accelerated dephasing, as is shown in this graphic. And what happens not only in the middle voxel, but near the edges of the middle voxel in the adjacent voxels, you have a difference in magnetic fields, which are shown by the orange lines, and you end up with a gradient at the edges between the central voxels and the magnetic field gradient, leading to a difference in precessional frequencies in this border zone. This leads to dephasing, and you get a phenomena which many people call blooming. You get signal loss not only in the middle voxel, but in the voxels adjacent to the middle voxel. And you end up with an image that looks like the one shown at the bottom, where not only the middle voxel is darker than you would expect it to be, but that darkness extends into the adjacent voxels, or blooms into the adjacent voxels. Can you distinguish materials that increase susceptibility, that is, paramagnetic materials, from those that decrease susceptibility, the diamagnetic materials? The answer is yes, because paramagnetic materials and diamagnetic materials affect the phase of the signal in opposite directions. This brings us to a discussion of the magnitude and phase components of the MRI signal. So we're going to back up a step and take a look at how the signal is generated in the MRI receiver coil, how that voltage is induced, and then look at 2 different coordinate systems, the Cartesian coordinate system and the polar coordinate systems, and then talk about the real and imaginary components of the MRI signal and the magnitude and phase components of the MRI signal. You will recall, if you saw the first lecture on basic MRI physics, that the magnetization can be represented by a vector that has a magnitude and a direction. And as it spins beside the MRI receiver coil, it induces a voltage which has a magnitude, but also has a phase, which goes from 0 to 90 to 180 to 270 to 360, and that cycle repeats itself. So it has a magnitude and it has a phase. This signal is generated by this time-varying magnetic field that induces this oscillating electrical voltage in the receiver coil. Most MRI scanners actually measure the MRI signal with 2 or more coils, and when these coils are oriented perpendicular to one another, They are called quadrature or circularly polarized coils. And the convention is in a lot of electrical engineering to call the axis along in the x direction the real axis, and the axis along the y direction, which is shown at the bottom left as the imaginary axis. And when you have pairs of these quadrature coils offset at 90 degrees to one another, you are capable of extracting the full phase information from the MR signal. So you can get the magnitude and the full phase of the MR signal with some relatively simple mathematics, which is going to be shown in the next few slides. So let's just look at the Cartesian and polar coordinate systems on the right-hand side of this slide. You can see that in the Cartesian system, you have the x and y axes, which in electrical engineering are typically called the real and imaginary axes. Or you can represent the same blue vector, the magnetization vector, in the polar coordinate system, where the length of the vector is called the magnitude, and the phase difference relative to the baseline is called the phase angle. And when you measure the MR signal, you actually get the signal in the real and imaginary axes, as is shown in the top row of images. And you can calculate the magnitude and phase of the signal with some relatively simple trigonometry, which is going to be shown in the next couple of slides. So to just review this topic one more time, we have the x and y axes in the Cartesian system and the magnitude and phase in the polar coordinate system. We place coils, a pair of coils along each one of these two axes. We apply a magnetic field gradient. We measure the signal, and we get a pair of signals, one from the coil at the top and another signal from the coil at the right. So the imaginary signal and the real signal. And that information is recorded in with the MRI data. How does one actually calculate the magnitude and phase components from this data? Well, you apply some mathematics and you get the magnitude and phase. And the next slide shows this mathematics. It sort of comes down to basic trigonometry, where the magnitude vector is the square root of the real and imaginary vector squared, sort of comes from the Pythagorean theorem. And the phase angle is the arctangent of the imaginary over the real magnitudes. So every time you measure the MR signal, you can get these four components. And on some scanners in previous years, you had a choice of displaying the real signal, the magnitude signal, but you also, in theory, have the possibility of displaying the imaginary or signal or the phase angle. We're only going to talk about the phase angle from this point forward. So if the bulk magnetization vector relative to the baseline has a positive phase angle relative to a baseline, it's called paramagnetic, which is shown orange in this slide. And if it's negative, it's called diamagnetic, shown as green in this slide. So the magnitude and phase components of the signal are always available, but the custom is only to display the magnitude of the signal in the vast majority of cases. But the MR signal also has a phase. The phase information is usually discarded, but in some instances, the phase can yield useful information in some cases and can be used to problem solve in some cases. So why is the phase image so rarely displayed and used? Well, it's because it looks like this. There's a lot of things that contribute to the disturbing parts of a phase image. This is actually an axial image of the head through the level of the brainstem, but superimposed on this is you have this low frequency information that goes across the entire image from bottom to top or from top to bottom. This caused by non-uniformities in the applied field. This typically is in the range of 5 to 8 cycles per field of view in most MRI scanners. So this unpleasant low frequency information is usually makes these images of little use and therefore rarely displayed. So all MRI imaging systems have this magnetic field uniformity that varies over the field of view when scanning body parts. This non-uniformity arises from imperfections in the magnet. They vary slowly over large distances in the magnet bore, somewhere in the range of 3 to 5, perhaps 6 or 7 cycles across the whole image. They are a nuisance and are never diagnostically useful. However, the non-uniformity arising from magnetic susceptibility effects between different voxels in the tissue can vary between each voxel in the image. This frequency of variation is relatively high, usually in the range of 100 Hertz across the field of view. This high frequency information can be diagnostically useful in providing a different type of image contrast. And that image contrast is part of the susceptibility weighted images, usually in the phase component part of the susceptibility weighted images. So what we've got coming out of the scanner looks like the image on the left, but what we want is we want to get rid of this low frequency information and end up with an image that we see on the right. The way this is done is a filter is applied to the image. It's called a high pass filter that lets the high frequency information pass and the low frequency information is eliminated. This rids the phase image of phase changes imposed by the non-uniformities of the magnet's field and uncovers the phase changes created by differences in the tissue susceptibilities, making them more obvious. So we want to get rid of that low frequency information that masks the useful stuff. Let's take a look at this graphically. So this is a conceptualized schematic. We have a magnitude image at the top and a colorized phase image at the bottom. And in the middle of that phase image, we've placed a very small black dot. If you look at the phase image, we have a full cycle of color variation from the bottom to the top, going over the whole spectrum of colors from blue through to red at the top end of the image, which is shown by that arrow there. And in the middle, we have a disturbance in that color scheme, that little black dot. So we have a low frequency, one cycle variation across the whole image, and a single voxel disturbance in the middle. So if you break down that image, you have a low frequency component and a high frequency component. You then apply the high pass filter, you get rid of that low frequency information, and the image looks like the one you have on the bottom right. You highlight that single black dot and you get rid of everything else by the application of that filter. Let's look at an example of how this is applied. So on the left, you have the magnitude component of a long echo time gradient recalled T2 star weighted image, which we would call a susceptibility weighted image. We get the phase component of that same image, but without the application of the filter. we can see that low frequency contamination across the image as that series of broadly spaced black and white stripes across most of the brain, and then more closely spaced black and white stripes near the edges of the skull. A filter is applied, it removes the low frequency information, and lets the high frequency information pass through, and what we have would be called a filtered phase image, which in some cases can be very useful and give us information about what's in the image that we're looking at. Phase images have a clinical utility in characterizing tissue. They add another type of image contrast to assist in characterizing some tissues based on their signature, their MRI signature, and therefore they can aid in differential diagnosis. For example, calcifications are diamagnetic, and on our scanner, diamagnetic materials are displayed as negative. So if we see a dark material on a phase image, we would conclude is diamagnetic. The most common diamagnetic material in human tissue is calcifications. If we see a positive phase change on the phase image, i.e. the material looks bright on the phase image, we would conclude it's paramagnetic, and on our scanner, we would conclude that's either blood, hemosiderin, iron, or some other blood breakdown product, which are the commonest types of paramagnetic materials on non-enhanced images. I'm going to show you some examples of the clinical utility and possible applications of looking at the magnitude and phase components of signal together when we have T2 star weighted images. I'm going to run through 3 or 4 examples. There are several articles in the literature which are much more extensive with respect to clinical applications, and I will refer to them at the end of this lecture. So in this example, we have a T2 weighted spin echo image at the bottom left. And then we do T2 star weighted gradient echo image. We'd call this a susceptibility weighted image. And we see several black dots on these images shown by the black arrows, which are escape detection on the spin echo image, because the gradient echo image is more sensitive to the dephasing effects of whatever material is causing those black dots. We now look at the phase component of that same image. We see that some of the black dots are white and some of the black dots are black. As illustrated here, we would conclude the white dots are paramagnetic and therefore likely blood or blood breakdown products, so little microhemorrhages, whereas the black dot is calcification in the choroid plexus. Another example, we have the T2 weighted spin echo image on the left, the T2 star weighted gradient echo image next to it on the right, and we display the magnitude component. We see a large amount of low signal intensity lesions that escape detection on the spin echo image. We now look at it in conjunction with the phase image. We see that almost all those areas that are black on the magnitude image have a positive phase change. We would conclude that they're paramagnetic, and we would go on to conclude that these are probably blood breakdown products, and these are due to diffuse axonal injury with microhemorrhages. We make that conclusion based on their distribution. And on the CT scan, we see nothing in these areas, as is usually the case with these small microhemorrhages. Another use is that In a lot of our brain tumor follow-ups, we skip the unenhanced images in order to speed up total imaging time. So this is a brain tumor patient, 1 week post-op, contrast enhanced T1 weighted spin echo image. We see that area of hyperintensity in the left cerebral hemisphere. On the susceptibility weighted images, the magnitude component, we see that part of that bright area is dark. The posterior part, we would conclude that that is blood, whereas the area that is anterior and medial to the dark area in the magnitude image, we would conclude that's contrast enhancement. You can see that at the levels of gadolinium that get into tissue post intravenous contrast injection, the amount of contrast agent that gets into the tissue is usually of insufficiently high concentration to cause a phase change. So on the phase image, we don't see any change in signal in the area of the contrast enhancement, but we do see areas of positive phase change in the area of the hemorrhage. And if we compare this post-op image at the top left with the preoperative gadolinium enhanced image on the bottom right, we would see how the two correlate. That area of contrast enhancement that we saw in the pre-op image has actually grown a little bit bigger 1 week post-op, whereas the more posterior component has been resected and there's hemorrhage in the surgical cavity. Note the shine-through effects of gadolinium on the T2 star weighted image magnitude component. So even though we call this T2 star weighted, we still can get shine-through effects, both T1 shine-through and T2 shine-through. That should be kept in mind when one looks at these images. The magnitude components of the T2 star weighted images are very useful also in displaying veins. Veins contain normal veins contain deoxygenated hemoglobin, so they have very strong dephasing effects on the signal, and they show up as dark on these magnitude images. Another potential use is when dealing with arterial venous shunting, where oxygenated blood gets into the venous system. This is a AVM in the right parietal region. You can see that collection of blood vessels. And along the bottom row of images, I'm showing you the magnitude component of the T2 star weighted images. You can see that the larger vessels, which look like veins, have high signal within them, whereas you would expect low signal in normal veins due to deoxyhemoglobin. This high signal is due to the presence of oxyhemoglobin and is an indicator of abnormal arterial venous shunting, where oxygenated blood is getting into the venous system. And that's shown and confirmed with the subsequent images. You can see that large vein draining cephalad into the superior sagittal sinus. And you can see the same on the catheter angiogram as is illustrated here. So another potential use. So I'm just going to go full circle here and just look at what is susceptibility weighting in MRI. So in my lexicon, weighting means the emphasizing of differences between tissues to achieve maximum image contrast based on the property of interest, whether it be the T1 relaxation, the T2 relaxation, or the magnetic susceptibility. So weighting for susceptibility means creating images that emphasize differences in magnetic susceptibility. In my opinion, the way we and vendors use the terms related to susceptibility to weight images is imprecise and bordering on incorrect and can lead to wrong conclusions. When we look at the magnitude components of these images are more weighted by the dephasing effects that are occurring in those voxels rather than magnetic susceptibility effects. So the clumsy term of magnetic heterogeneity weighted images would be more accurate, but that term is really never used. Nevertheless, SWI, susceptibility weighted images, are useful, and even more so when all the component parts of these images are analyzed. A specific type of susceptibility weighted image has been implemented on one vendor's MRI system. So let's just take a look at how these SWI images are made. Other vendors have different implementations of the same idea. So first of all, a T2 star weighted sequence is done. Both the magnitude and phase components are calculated and can be shown as separate images. And then they are combined to form a hybrid image, which is the SWI image. So let's take a look at this. The magnitude image is shown on the left. The phase component of that image after the high pass filter is shown in the middle. A mask is created out of that phase component, and then the magnitude and phase components are multiplied on a voxel by voxel basis, and it creates what the vendor calls as the SWI image, as shown on the right-hand side of this slide. The SWI image looks a lot like the magnitude component of the original T2 star weighted image. If we look at this example here, we have the phase component at the upper left, the magnitude component in the center, and the SWI hybrid image at the bottom right. You can see that the SWI magnitude components look very, very similar, but they are subtly different. In my opinion, the mask's most often observed and intended effect is to make tissues that are dark on the magnitude component image and that are also paramagnetic and hence positive on the phase image look darker on the SWI image compared to the magnitude image. So if you look at each one of those dark areas that are bright on the phase image, they look darker on the SWI compared to the magnitude image. Let's look at another example on this slide. So here we have a small lesion to the right of the falx, which on the magnitude component has a bright periphery. This is in a contrast enhanced image, so the brightness is due to intravenous contrast. The center is dark. When we look at the phase component, the central part that's dark on the magnitude is very bright, hence it on the phase image, it's paramagnetic. When we combine the two effects to create the SWI image, we see that the dark center becomes even darker when the phase component is hybridized with the magnitude component. We will conclude when we look at all these images together that the center of this lesion contains blood breakdown products. Let's now look at some additional features when we analyze phase images, which makes their analysis occasionally more complex. We're going to look at the effect of aliasing and the effect of the high pass filter on the appearance of some lesions. So on MRI phase images, a grayscale is used to show the phase change created by paramagnetic and diamagnetic materials. And the conventions vary between MRI scanners. On our particular scanner, paramagnetic materials are shown as a positive phase change. With some other vendors, the opposite is true. So in the example I'm going to show you, the grayscale is assigned in the following way. If there's no phase change relative to background, the grayscale is shown as a neutral gray, which is the starting position of the blue arrow you see in the graphic at the bottom. If we create a positive change, the grayscale is designed to show that material is whiter, and if it's a negative phase change, it's shown as blacker. Let's take a look. So if it's a positive phase change, it becomes whiter, and the arrow gets pushed to the maximum degree of whiteness, as shown at the bottom of this slide. If we now take a diamagnetic material, it creates a negative phase change, and that change is shown as progressively blacker and blacker until we get the maximum blackness allowed by the grayscale. Well, what happens when we exceed the limits of the grayscale? Let's take a look at this slide here. It keeps going around. This effect is called aliasing. So at some point of maximum whiteness, the material would jump and be shown as suddenly black. This is called aliasing, and the opposite effect occurs in the other direction. So if we take a look at a phase image as is shown in the upper right, and let's magnify the area of maximum aliasing. I'm going to take that little bit and show it down here. And if we look at this slide, this component of the slide, as we move from left to right, we can see that it goes from neutral gray to very white, then it suddenly becomes black, then becomes neutral gray, becomes whiter, suddenly black. So we get aliasing at these transition points between maximum whiteness due to aliasing. So this happens because as we get further and further in this direction, there's a higher and higher phase change which exceeds the grayscale. So we get this aliasing effect. Let's take a look at how this affects the interpretation of certain images. Here we have a cerebellar hemorrhage. I'm showing you the magnitude image at the top and the phase image at the bottom. I'm going to magnify the phase image. So if we look at this area at a high level of magnification, you'll notice the same type of aliasing effects. We get these transition points where it goes from neutral gray to very white, then jumps to black, goes back to gray, very white, jumps to black. And this is because we get this progressive phase change across the image as we move from the neutral background across the image. The phase change is greater than what the grayscale can handle, so it aliases and you get these peculiar banding patterns due to aliasing across the center of the image. Let's look at another example. Here we have a hemorrhage in the left temporal lobe. If we look at what happens to the phase change, let's just say what happens when all the voxels within the lesion have approximately the same degree of phase change, say hovering between 150 and 180 degrees of phase, so you don't get aliasing. If we look at the phase component of this image, what we can see is that the center of the lesion looks just like the background, and that's because of the filter. So we're going to magnify that up. If we look at the image as we move from outside the lesion to the edge, we get a positive phase change due to the presence of blood, and so it shows up as white on the phase image. I'm going to magnify it further. So I would conclude in this particular instance, although I have no proof of this, that we have a phase change at the edges of the lesion to near the maximum allowed by the grayscale, but the the phase change probably plateaus in the middle of this lesion. It does not increase any further. So there's no variation in the image, and the high pass filter kicks in and only lets the high frequency information through. It removes the low frequency information from the center, and we end up with the center of the lesion looking a lot like the background because the background's been filtered out due to the high pass filter. So we have positive phase change relative to normal brain at the edge of the lesion. The high pass filter lets us in high frequency information pass, but we have approximately the same phase across the whole central part of the lesion. The high pass filter filters this information out, and the center of the lesion looks like the background. Let's look at this example. This example will show the aliasing effect on the phase images at the edge of the lesion and the high pass filter effect in the center of the lesion. And I will graphically show what I think is happening when there is changing phase versus constant phase in the presence of a high pass filter. This pair of images shows the magnitude and phase components of a patient with a left frontal lobe microhemorrhage. These images are magnified at the bottom of the left-hand side of the screen, and then I further magnify the phase component at the top right of the screen. What we're going to do is we're going to start at the left-hand side of the lesion, move across the lesion to the edge where we'll see aliasing from white to black, back down to neutral gray, gray across the center, and then black to white and back to neutral gray. If we draw a series of arrows across this image from left to right, we'll see this. We'll see a gray arrow across the background, a transitioning white to black arrow at the edge where there's aliasing, gray across the center, the reverse gray to black to white arrow at the other edge of the lesion, and then gray when we get back to the background on the far right of the image. If we were to graph what is happening here as phase as a function of position, moving from left to right, what I think happens is in the background, there's no change of phase, so it looks gray. When we get to the edge of the lesion, the paramagnetic effect of the iron causes progressive whitening till it aliases. In the center, there's still a high phase difference, but it doesn't vary across the center of the lesion. So the high pass filter removes it and makes it look like background, and then we get the opposite effect at the right-hand side of the lesion. So we have increasing phase. The increasing phase, if it goes beyond the point of aliasing, we get a transition from white to black. There's little phase difference across the middle. So we have the high pass filter effect that removes the low frequency phase information, then the opposite on the right-hand side of the lesion, and then back to back. Quantitative susceptibility mapping is a method in which the phase information can be displayed over a continuous grayscale with an algorithm that removes the aliasing effects and the high pass filter effects that we've seen in the previous images. There are many methods of doing quantitative susceptibility mapping. This is one of them that I think shows the capabilities very elegantly. And these methods are designed to be able to quantitate the amount of tissue iron or tissue calcium on a voxel by voxel basis. I will show you one of the references for one of these methods at the conclusion of this lecture. So to summarize, magnetic susceptibility chi is the degree to which a tissue magnetizes in an applied magnetic field. The simplified formula is chi is equal to the induced magnetization over the applied field, but as I mentioned at the beginning of this lecture, this is a simplification. The term susceptibility weight images is a misnomer and can be misleading. Most of the image contrast in images that we call susceptibility weighted, at least the magnitude component, are mostly due to dephasing differences rather than susceptibility differences. The image derived from the phase component of the signal is the one that is most susceptibility weighted of the lot. The imaging sequence I consider a niche sequence. It helps with the detection of some lesions that have strong dephasing effects. It helps with problem solving, and it helps with differential diagnosis. This pulse sequence yields the most information when the magnitude and phase components are analyzed together, and one must remember the confounding effects of aliasing and that high-pass filter unless you have some processing method to handle those potential confounding effects. I have found the sequence useful for detecting calcium, blood, hemosiderin, and other blood breakdown products. It helps in the differential diagnosis of calcium versus blood and blood breakdown products. I have found it useful in the differential diagnosis of the appearance of lesions when only enhanced images are available and non-enhanced images are not available. You can dissect out the effect of the contrast enhancement versus the effect of the blood. It is also useful in looking at arteriovenous malformations and arteriovenous fistula to determine whether or not oxygenated blood is present in the venous system. These are four references that you may find useful. The article by Heike is an excellent technical description of susceptibility weighted images. The others are some clinical applications, and the bottom reference by Wang is a detailed discussion of quantitative susceptibility mapping. That's the end of the lecture. Thank you for your attention.